for each possible microstate of an electron configuration, we can write a Slater determinant. And if you apply perturbation theory to get a better accuracy, a better way to account for electron-electron repulsion, then you take linear combinations of these Slater determinants, and that will give you terms. And we said that a term, a set of these microstates that have the same L and J, okay, I mean L and S, I'm sorry, would correspond to a term. Okay? So, for example, when we have a term that says something like doublet P, okay, what does the P stand for? Quantum number L being equal to 1, and the 2 here, the multiplicity, that's the value of 2s plus 1. That means s is equal to 1/2 in this case. So what we're saying is that the total orbital angular momentum of your electrons would be square root of L times L plus 1 h bar, right? And the total spin angular momentum of your electrons for this particular term would be square root of s times s plus 1 h bar. Okay? And the degeneracy of this term would be 2L plus 1 times 2s plus 1, right? So 2s plus 1 is 2, and 2L plus 1 is 3. That would be 6. So a doublet P term would be a term that is comprised of 6 quantum states. All right? Now, that is, up to that point, we have been ignoring spin-orbit interaction. And we talked about spin-orbit interaction earlier when we talked about hydrogenic ions and the hydrogen atom. So we need to get a better accuracy as far as trying to match experimental data. We have to take into account spin-orbit interaction for atoms with more than one electron as well. Okay, so let's review what spin-orbit interaction was. You said that because of the orbital motion of your electron around the nucleus. Okay, so imagine you're sitting on an electron and you're moving around the nucleus. It would appear as though the nucleus is moving around you, just like we here on Earth, we're going around the sun. It would appear as the sun is going around us. So as far as an observer at the electron, there appears to be a charged particle, the nucleus, that's going around it. Okay, so that charged particle generates a magnetic moment, and so that magnetic moment will interact with the electron's intrinsic magnetic moment. Okay, so that leads to an additional potential energy term that you have to add to your Hamiltonian, so we can treat that as a perturbation. And that additional potential energy term is directly proportional to the dot product of the spin angular momentum vector and the total orbital angular momentum vector. Okay? So that's why we refer to this correction to our Hamiltonian as being due to spin-orbit interaction. Now, it's directly proportional to that dot product. The proportionality constant depends on the charge of the nucleus. So the greater the charge of the nucleus, the more we cannot ignore spin-orbit interaction. Okay, this tends to be small for hydrogen, helium, but as you get to large atoms that have more protons in the nucleus, the spin-orbit interaction is something that you can no longer ignore. Okay, so the first order perturbation correction term, if you apply perturbation theory, will be given by this expression right here. It's hc times some constant a times j plus 1 minus L times L plus 1 minus S times S plus 1 times, this is just h bar squared, okay, h over 2 pi squared. Now this A right here is your proportionality constant, and like I said, that depends on the charge of the nucleus. So that depends on the strength of the spin-orbit interaction. This L right here, we already know what that L is. For a doublet P, what is L? For example, L would be L is 1. And your S, what's our S for a doublet P? It's going to be 1/2, right? 2s plus 1 is 2. Now, J here is the quantum number for the total angular momentum. So it's J, your total angular momentum is just the sum of your orbital angular momentum and your spin angular momentum. Okay? And so, as a consequence of that, okay, we can take linear combinations of wave functions associated with a given term to get what we call levels. So these energy levels will depend on J. Okay, so for a given L and S, you're going to, all quantum states that have the same L and S from a given configuration will belong to the same term. Okay, but these quantum states in a given term, they're not going to actually have the same energy if we take into account spin-orbit interaction. The actual energy would depend on the quantum number J. So this allows us to further split the degeneracy into what we call levels. So a given J level, a given J will be associated with an energy level for an atom. Okay? So linear combinations in the same level will have the same J. So we can modify our term symbol by attaching a J as a subscript next to the term symbol. So for a triplet P, for example, a particular level might be something like triplet P2. So this 2 right here, the number down here, that's your J level. Okay, so if I have a triplet P2, let's just clarify this. This comes from a triplet P term. What is our L? L is 1, and 2s plus 1 is 3. It's a triplet, so therefore S is equal to 1. Okay? So if it's a triplet P2, this is a particular quantum state that has J equals 2. Right? So how do you determine your levels? Let's look at it for a triplet P. Let's look at the doublet P here. That's just the example that's given here. So let's say you have a doublet P term. What's our L for this one again? 1, and our S is 1/2. So what are our possible M sub L's and M sub S? M sub L can be 1, 0, or -1. And what are our possible M sub S? Positive 1/2 and -1/2. So what do you get? M sub L plus M sub S would give you M sub J, right? The Z components of your angular momentum vectors will just add up. So the possible components of your angular momentum vector along the Z-axis would be M sub J H bar. Okay, and what are the possible M sub J's we can have? What is 1 plus 1/2? 1.5, that's 3/2, right? What is 0 plus 1/2? That's 1/2. -1 plus 1/2? -1/2. 1/2, 1 plus -1/2 is positive 1/2. 0 plus -1/2? -1/2. -1 plus -1/2 is -3/2. Okay? Since your M sub J's go from J all the way to -J, we look at the largest possible M sub J that we have here, which is 3/2. So that must be part of a set that goes from 3/2 to -1/2. So you have 3/2. 3/2 to -3/2. So from 3/2 to -3/2. So what's 3/2 minus 1? 1/2, and 1/2 minus 1 is -1/2. So this corresponds to J equals 3/2. So that takes care of 4 of those. 3/2, 1/2, -1/2, -3/2. Of the remaining M sub J's, what do you have? 1/2 and -1/2. So that must be part of a set that goes from 1/2 to -1/2. So that means of the remaining M sub J's, which is 1/2, that must be you have a set that goes from 1/2 to negative 1/2. That must correspond to j equals 1/2. Okay? So for a doublet P, okay, if you apply a correction because of spin-orbit interaction, a doublet P term is going to split into two levels, okay? A doublet P 1/2 and a doublet P 3/2 level. What's the degeneracy of the doublet P 1/2 level? 2. There's two possible m sub j's. M sub j equals plus 1/2 and m sub j equals negative 1/2. What's the degeneracy of the doublet P 3/2 level? 4. 1, 2, 3, 4. That would correspond to m sub j of 3/2, 1/2, negative 1/2, and negative 3. Right? So that's how you determine the levels. Now the quick way is just to use the Krebs-Gordon formula. Okay, all you have to do is the allowed j's would just be L plus S all the way down to absolute value of L minus S. Let's do that. J equals, what's L? 1 plus 1/2 all the way down to 1 minus 1/2 L minus S. So what are possible j's? So that's going to be 3/2 all the way down to absolute value of 1 minus 1/2 is 1/2, right? So our possible j's are just 3/2 and 1/2. So same thing, okay? So this is the shortcut for what we just did earlier. So the degeneracy of each level is 2j plus 1. You're going from m sub j equals j to negative j. This is the example. Okay. Let's try another example. Let's try triplet P. What if you have, let's do a triplet D. What would happen if you have a triplet D term? What's our L? L equals 2. L equals 0 for an S term, it's 1 for a P term, it's 2 for a D term, it's 3 for an F term, right? So L equals 2. What is our 2S plus 1 here? What's our multiplicity? 3. So that means what is our S? Our S is 1. Okay? So what levels can we get for a triplet D term? L plus S all the way down to absolute value of L minus S. So those are the possible J values. So that's going to be 2 plus 1 all the way down to absolute value of 2 minus 1. And so that gives us 3 all the way down to what's absolute value of 2 minus 1? 1. So 3, 2, and 1. So a triplet D term, once you apply spin-orbit interaction correction, breaks up into 3 levels. What are those 3 levels? Triplet D2, triplet D3, triplet. Okay, you got a triplet D3, triplet D2, and triplet D1. Okay. So that's how you get your levels from a term.